All right, in the first video, we talked about the method that we're going to use. Now let's use the method with a simple, well, I say simple, it's not going to feel simple, with an area example. So we have got the manager of a garden store, and that manager wants to build a 600 square foot rectangular enclosure. Before we read any further, remember our steps. Translate the problem into a picture and into math. Sometimes you want to get through the whole problem, but for me, I like to do this while I'm reading the problem. Let's just write things down, underline things. The manager wants to build a 600 square foot rectangular enclosure. We've got a rectangular enclosure. I know it needs to be 600 square feet. We can always change this picture later if we get new information, but let's just start writing some stuff down. It's on the parking lot in order to display some equipment. All right, that's probably just for context. I don't think that's going to be a part of the math. 3 sides are going to be built with redwood fencing. Okay, that's important. 3 sides are redwood fencing. Let's have this one. This red is going to be $7 per foot. Let's write that down. The 4th one will be of cement blocks. So these are my very lovely cement blocks. And that has a cost of $14 per running foot. Okay, good. Find the dimensions of the least costly. Okay, least costly. What are we trying to minimize or maximize? That tells us that we're trying to minimize the cost. Okay, now we've done a lot of the stuff. We have a picture. We wrote down the important information in math. There's a little bit more that we can do, but let's just stay here for now. Let's look at step 2. Identify the objective function and its domain. Okay, so the objective function is what we're trying to minimize or maximize, right? This is our objective function. Now we need to actually write it out. So cost, what does cost depend on? Let's leave that part blank for now. Just write it C for cost. What is the cost of building this thing? Well, for every foot of the red, it's costing $7. For every foot of the black, it's costing $14. We need some variables, right? Now you could let X be how many feet of red and black, and like Y be how many feet of the black. That would work. But with our picture, it's going to be a little bit easier to just have X and Y be length and width. You could do length and width, L and W, X and Y. There's also multiple ways of setting up this problem. Okay. You could do this be X and this be Y. All right. Lots of different ways of doing this. This will probably be the easiest way. If that's our X and our Y, what is our cost? Well, it's $7 per every foot. $7 for every foot of the red. How much red feet do we have? Well, we have 1x of red foot, and we have 2y of red foot. So what is this, right? This is $7 per every foot. So this is our cost, right? This is cost per foot. And this right here is the number of feet. The bottom, which is x, and both sides, which are each y. And we have y plus y, so that's 2y. Now we just do the same thing for the other one, right? 14 feet for the cement blocks. How many feet of cement blocks do we have? X. So now our objective function has 2 variables. We can't use calculus yet to minimize a function of 2 variables. We won't be doing that in this class, but in other classes, you can use calculus for however many variables. Right now, we just do 1 variable at a time. So let's simplify by distributing. we're going to have 7x plus 14y plus 14x. And now we can collect like terms. Our cost function is 21x plus 14y. And I just want to like highlight it a little bit. We're not really, this is not our answer. Maybe I don't even want a box, right? Let's just maybe highlight or do something. This is important. Maybe we underline the answer. However it makes sense for you to do it. But just make sure, okay, this cost function is important. So we've identified the objective function. We also need its domain. What are the inputs that make sense? All right. Well, the inputs that make sense are, well, x is a length. And x has to be positive. X being 0 makes no sense. And y has to be positive. There's a little bit more going on here. There is a maximum. X can't be 1,000 feet. Really? Sort of. I guess technically it could if y was like 1/6 of a foot. I guess technically this is our domain. I guess technically there's not a maximum. Mathematically there's not a maximum, but realistically there's a maximum. So you can decide whether you want to write it or not. Okay. You'll get the same answer either way. Good. So again, we did this. We did this. Do we have 2 or more variables? Yes, we do. Find the constraint equations. This is where we're at now. Maybe there's only one constraint equation. What is our requirement here? We can't just build any parking lot. Apparently, we don't have a requirement on funds, which is nice. We can spend as much as we want, although we do want to minimize the funds. The only other requirement they tell us is that the area should be 600 square feet. All right, so again, as a reminder, this is our objective function. Our constraint, our requirement, is that we need the area to be 600 square feet. Well, what's the area? It's x times y. That means x times y has to be 600. This is our constraint equation. This is our only constraint here. Usually we'll only have one. Ta-da! We've done this step. We found the constraint equation. Now 2B says solve the constraint equation for one variable. Substitute into the objective function. So do you want to solve this for x or y? Doesn't matter. It'll look different, but it doesn't matter. You could solve this for x or y. I like solving things for y most of the time, but it's up to you. So to solve this for y, we have to get y by itself. Let's divide both sides by x. The left-hand side that cancels and y is by itself. The right-hand side is 600 over x. Okay, we did the first half, right? We solved for one variable. Now we need to substitute into the objective function. Here's our objective function. Let's substitute. C was 21x plus 14y. And now we're substituting, right? Y is just 600 divided by x. Great. Let's simplify a little bit more. Now we have 21x plus 14 times 600, 8,400. Not leave this up to chance. 8,400. Great. 8,400 divided by x. Now we have a new objective function with only one variable, which is really nice. Because we can use calculus on this. And again, We need x to be positive. That's really our only requirement, because y also had to be positive, but y will be positive exactly when x is positive. All right, so that's our domain. Whew, good. As you can see, these problems can sometimes get a little long. That's why this whole section's videos is just me doing problem after problem after problem. Try to give you an idea of my problem solving strategy and give you practice seeing me apply it to different things before you go and apply it to different things as well. Not all of the homework problems will be identical to any of these problems. You're going to have to apply the strategy, because the fact of the matter is, in life, right, there's 5 million different types of problems out there anyway. So step 3, it's finally calculus time. It's funny because you probably will all be happy when you finally get to calculus time. Probably not something you would have thought of last year or something, okay? Yeah, now we just find global extrema. We'll check the critical points and the endpoints. All right, so this is our objective function. We just need to minimize cost. This is why I'm not in business myself. If I'm maximizing costs, oh gosh, right? What did we want to do? We wanted to minimize this. Now it's just a 2.7 problem. Just a 2.7 problem. Okay, so let's get into it. We need to find critical points and endpoints. We better hope it's not at the endpoints. We didn't actually make a big deal out of this. We only found global extrema for closed intervals. This is technically an open interval. I'll address that a little quickly. Okay, so critical points. Critical point is when the derivative does not exist or equals 0. We need the derivative. So C prime is our derivative. Usually we would write C of x as a function. But if you just want to write C prime like that, that's fine. The derivative of 21x is just 21. Ooh, what's the derivative of this other thing? Let's rewrite it real quick. Right, C of x is 21x plus 8400 times x to the negative 1. Let's take the derivative in this form, so we can use the power rule on that second one. The exponent comes down. So now we have a minus 8400. Now we subtract 1 from the exponent. So now we have an exponent of minus 2. Let's rewrite that without the negative exponent, make things a little bit easier to work with. Remember, the negative exponent moves the variable to the bottom. This is not what we have. If we had this with the parentheses, everything would go onto the bottom. But because we only have this, remember your order of operations, this is really what we have. Only the x goes to the bottom. All right, when does this not exist? And when does this equal 0? Well, it doesn't exist when what? It doesn't exist when x is 0. Why not? Anytime you have a fraction, if your denominator is 0, that's undefined. Okay? So it doesn't exist when x equals 0. This is a critical point, but it's not a critical point that we care about. Not a critical point that we care about because this is our domain. Right? This is our domain. So this is not in the domain. So we don't care about it. Not important. And in fact, the function doesn't even exist there. We can't have an area with a side length of 0. Okay, we also need to find out when is C prime equals 0. So, okay, C prime equals 0. When, well, let's set it equal to 0. If C prime is 0, the C prime literally becomes the 0. And now we have to solve this rational equation. All right. So we've solved rational equations before. If you're a little fuzzy on your rational equation solving, that's no problem. One of the best ways to solve rational equations is to multiply both sides of the equation by the least common denominator. Another way of doing it would be to add this to both sides so we get the variable by itself. Multiple ways of doing it. The most consistent way is to multiply both sides of the equation by your least common denominator. This works with any equation with fractions. Any equations with fractions, hypothetically, if you didn't like fractions, you could just multiply both sides of that equation by the least common denominator. Left-hand side is easy. 0 times x squared is just 0. Right-hand side gets distributed. 21x squared. When we multiply the second one, the x squareds cancel. We're just left with 8400. And now this is has no more fractions. This is just a quadratic equation now. You could use the quadratic formula, or because there's no x term, there's only an x squared term, we can just add 8400 to both sides to get our variable by itself. So 8400 equals 21x squared. Let's divide both sides by 21. I'm going to go through this a little quickly. 21, I think that's 40. 100. I don't trust myself. 8400 divided by 21. Okay, it is 400. Great. And now we need to take the square root of both sides. Whenever we take the square root of both sides, we do need a plus or minus sign. And I believe that's 20. It is indeed 20. So again, mathematically, the solution to this equation is plus or minus 20. But only one of these numbers makes sense. Our domain, remember, domain is just the numbers that make sense. Negative 20 doesn't make sense for building a parking lot. All right. So again, negative 20 is not in our domain. We'll just say x is 20. Right. Negative 20 is not in the domain. So we have our critical point. The first critical point wasn't in the domain. We found a second critical point that wasn't in the domain. This is the only critical point that is in the domain. What were we doing again? I said it's easy to forget. We're using calculus to find the global extrema. We find global extrema by checking critical points and endpoints. Well, we found the critical point. We don't really have endpoints, but we can use the idea of limits to think about it. If we're looking at all numbers that are bigger than 0, then on a number line, right, 0 is here, all numbers that are bigger than 0 look like this. So the two ends are 0 and infinity, right? The left of this interval is basically 0. Well, basically 0 is not going to make any sense here. If you're really, really close to 0, this cost is going to be infinitely high. If you divide by a really, really small number, you get a really, really big number. Big cost is bad. And of course, if x gets infinitely big, this one. So our endpoints are going to be infinitely high cost. Okay. So looking at the cost function, x being 0, or x being infinitely big, have huge costs. So remember how we find an absolute or global extrema. We look at the critical point, we look at the endpoints and pick the smallest or the biggest. Here we want to minimize the cost. The endpoints are huge. Those are bad. You don't want to look at the endpoint. So this is going to be our minimum. And in fact, you could use the first derivative test or the second derivative test to show that this is our minimum. Great. So we will have a minimum at x equals 20. The calculus is over. Da, 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 da. This is important. What's our next step? Make sure we answer the right question. Translate your answer into English. We said x was 20. What were we trying to do? Find the dimensions of the least costly such enclosure. Oh, so x is 20. What is y? Well, if it needs to multiply to 600, y must be 30. Oh, I drew my rectangle wrong. That's fine. Right? So y is 600 divided by x. Let's find that real quick. X is 20. Y is 30 feet. Good. Also something that's important. Oh, I didn't do the big highlight. We found X and we found Y. Now we know what our dimensions look like. We can answer in English. So it actually looked more like this. It was longer. So, and the X, 20 feet. The Y was 30 feet. We should build, what is it called? Enclosure. We should build a 20-foot by 30-foot enclosure with the 20-foot side having the cement. The picture tells that, but let's just be really clear. For a total cost, how much are we actually having to pay for this? I said minimize the cost. Well, how much is it going to cost? We can use our cost function, right? Cost was 21x plus 14y. You could also use this one. I like this one. This one's a little easier. 21x plus 14y. 21x plus 14y. Cost is going to be $840. Whenever you're doing this question, and when I box my answer, I'm actually going to include the picture. Whenever you answer these applied optimization questions, your answer should make sense for somebody who's not in calculus. Your answer should make sense for somebody who knows nothing about calculus. Okay? The question is, find the dimensions of the least costly enclosure. This answer makes a lot of sense to anybody. We should, oh, well, outside of the English, we should build, I really set myself up for that one. We should build a 20-foot by 30-foot enclosure, the cement side being the 20-foot side, total cost $840. Here's the picture. Everybody knows what this means. All right. So we did step 4, translated it in English, make sure we answered in the right problem. And step 5 is just to make sure the answer makes sense. Does this make sense? It's 600 square feet. That's what we wanted. Good. Seems plausible, right? This side was most expensive, so this side should be shorter. And then like looking at the cost. Oh, and then this is interesting, right? The cost is double on the black side. The dimensions were 1.5 times. It seems ballpark. It just, all right, doesn't look obviously wrong. All right, let's pack it up, go home. Just a 24-minute problem. The more and more of these you do, though, the faster you're going to get. And of course, we spent some time explaining things as well. These problems will take less time as you get more skilled at them, and that's why we are spending a lot of time in this section. So let me know if you have questions. Reach out for help to me, and you have other resources as well. Best of luck, and have a good rest of your day. Good luck getting started on these.